Well, congratulations. We have reached the last section of chapter 4. I know chapter 4 has been very long and rather difficult, quite challenging, because we have been learning applications and theory related to different derivatives and differential calculus, right? So 4.10 is sort of like a game. We have been differentiating functions. So what happens if you want to go backwards, right? You want to find a function whose derivative is the given function. So that's like an opposite of differentiation, and you can just use it and think of this as, playing this silly game of, doing the inverse operation of differentiation. Well, it turns out the rest of this course, chapters 5 and 6, totally depend on this procedure, all right? And so this is called anti-differentiation, and the section 4.10 is called antiderivatives. So let's look at section 4.10. All right, so antiderivatives, we're going to do the opposite procedure, all right? So far we have been doing lots of differentiation problems. If you take x to the n, you get n times x to the n minus 1, right? Sine of x, d dx of sine of x is cosine of x, and so on, right? Let's do the opposite. And the reason why we do the opposite, it will be very clear once we get into chapter 5 and chapter 6. It's not just a, playing around and see, hey, can we do this opposite procedure? The question now is, given the function f, can you find a function whose derivative is that function? We will give a name to that kind of thing. Capital F of x, capital F of x is called an antiderivative, the opposite of derivative of fx, the lowercase f, if and only if the capital F, capital F is a function such that its derivative is that given function, lowercase f, for all x in the domain of the lowercase f. All right, so in this situation, we are going to be given some function f, lowercase f, and we'll find a function whose derivative is that lowercase f. Okay, so why do they use capital F and lowercase f? They're both pronounced f. That's really confusing, right? Yeah, right. So somebody should complain to these people who have established this as the norm or the standard or tradition in calculus. So we'll have to say something like the upper case, the capital F and the lowercase f repeatedly. Okay, now if f of x is 2x, can you think of a function whose derivative is 2x? Yeah, I think you can. X squared, right? X squared, the derivative of that is 2x. No problem. So this is an antiderivative of 2x. But so is plus 1, plus 2, and all that, right? So you can just add an arbitrary constant, and this will be all of the functions whose derivative is 2x. Okay, so this is actually going to be a family of functions. If you have to find all antiderivatives of a given function, lowercase f, it's always going to be family of functions. And they have that plus c added at the end of the other function. All right, so I'm going to give you another definition which appears in much later in the book, or much later in the section in the book. But given the lowercase f, some function, the family of functions, the family of antiderivatives, so you will write this as f of x, and then plus c. All right, so it's going to be something like this. Right? It's called, now watch this. Okay, it's called the indefinite integral of fx, and is denoted with this strange notation. Long S, this is called the integral symbol. Oops, what happened to the integral symbol? Watch out, it'll disappear when you're not watching. The integral symbol of fx dx, Okay, and this is called, you write fx plus c. All right, so where, and this is of course assuming that capital F is the antiderivative. So this is the notation we use. Okay, now there are several confusing things about this thing. First of all, why do we use the integral sign to just write something that's antiderivative? Well, again, it turns out what we call the method of integration or the process of integration, which is what you would be learning in chapters 5 and 6. It turns out to be very closely related to, and in fact, it is the same as the opposite procedure to differentiation. So it turns out, okay, antiderivative. I'm giving you a punchline. I'm sorry about this. I'm ruining this for everybody because I'm giving you the spoiler. But the point is, it turns out the opposite procedure to differentiation turns out to be the way to integrate a function, and that has to do with area under the curve and so on. But we will wait until chapter 5 to learn that. For right now, just understand that because those two things, the opposite of differentiation and finding the area under the curve called integral, happens to be the same procedure, and therefore we use this integral sign to indicate the opposite of differentiation. The other thing that's confusing is this thing here. What is that differential doing here? Right now, don't worry too much about this, okay? Eventually, we will express why this differential, dx, is here. But right now, just think this is the variable with respect to which we are finding the antiderivative. Right now, the plus c is always going to be there whenever you see this, the indefinite integral sign, and so just be aware of it. And the understanding is that capital F is a function so that its derivative is the lowercase f. All right, let's do an example of this. E to the x. Okay, so what functions can you think of whose derivative is e to the x? Think really, really hard. No, you don't have to do that, right? Because you know e to the x is that. Oh, but how about e to the x plus 5,000? Yes, of course. So all of these, and in fact, only these functions are such that their derivatives are e to the x. Okay, how about x to the fourth? What is the indefinite integral or the antiderivatives of x to the fourth? Well, in differentiation, you subtracted 1 from the exponent. But in integration, you have to add that. But if you differentiate this, you get 5x to the fourth. So you have to divide this by 5, okay, plus c. And so this indeed is the correct formula or correct expression for the indefinite integral of x to the fourth. All right, so when you do, like for instance, 2x dx, this is the antiderivative or antiderivatives of 2x, and that turns out to be x squared plus c. And notice here, that is the family of functions, family of parabolas, in fact, right? This is x squared, and then you have x squared plus 1, x squared plus 2, x squared minus 1. And so this is all going to be, every indefinite integral is going to have the plus c at the end. It's a family of functions differing by constant. Okay, so that's that. Here's a little theorem, so you can do a whole bunch of other problems. This theorem is so intuitive that if I didn't tell you that, you would automatically assume this. Okay, what am I talking about? Well, if the indefinite integral of lowercase f is capital F plus c, and if the indefinite integral of g is capital G plus c, then the antiderivative or indefinite integral of f plus g or f minus g is simply f plus or minus g, the capital letters, plus c. You don't have to write plus c twice, obviously, because that's just, you're adding an arbitrary constant. Also, if you have k times f of x, okay, What do you think this is? Okay, that's K times capital F plus C. And you don't have to write K times C because, again, C includes a whole bunch of, and in fact, all of the real constants. Okay, so with that, you can do a lot more problems. What do you think this is? The indefinite integral of x plus e to the 2x dx. I think the temptation that everybody faces here is because you have been so trained to differentiate and you have been spending so much time differentiating functions, you automatically want to do that. And doing the inverse operation is going to be difficult, right? So what function will give you the derivative, which is x? Right? That's like x squared, but not quite, right? It's over 2. It's 1/2 times x squared. And in fact, it's a great idea. And I do this to this day after, 40 some years of learning calculus. As soon as I take the antiderivative, as soon as I find the indefinite integral, okay, I automatically, almost always, mentally differentiate this. Okay, as soon as I write what I think my answer is, x squared over 2, I differentiate this, and I get 2 times 1/2 x to the first, which is that. Okay, so I get the right answer. Okay, let's move on. To get e to the 2x, what do I have to do? 2e to the 2x? No, because I can't. If I differentiate this, I get 4 times e to the 2x. So that's not right. So what is that? It's e to the 2x divided by 2. If I differentiate this, I get 2 over 2 times e to the 2x, which is exactly this, right? And not forget plus c. So that's, how you can find these. All right, here's one important example, which is maybe a little surprise, but this is what we do. When you are asked for the indefinite integral of 1 over x dx, so what is the antiderivative of the reciprocal function? Many times you see this written as dx over x because that's the same thing. All right, it turns out, it's the answer is natural log, right? ln of x and plus c, you can do that. Okay, but it turns out it's a little more than this because this is defined for negative values as well, right? So you want to include the negative values in the antiderivatives. And there's an easy way to do this, and that is this, surprisingly. And of course here, we have to make sure x is not 0, because if x were 0, this thing doesn't, 1 over x doesn't exist. So it's not defined. All right, so let's just make sure we are okay with this, right? I'm saying x could be any number except 0. If x is positive, right, natural log of the absolute value of x is exactly the same as natural log of x. Okay, so let's call this y. So the derivative of y, actually, let's call this capital F. Okay, so the derivative of that is 1 over x as expected or as desired, because that's what I'm trying to find the antiderivatives of. If x is negative, would it work? Well, according to this, I am supposed to have the absolute value, the natural log of the absolute value of x. If x is negative, this is natural log of negative x. Do you see that? Because negative x in this case is positive, because I'm assuming x is negative, right? So what's the derivative of this function then? It's 1 over negative x times the derivative of the inside function according to the chain rule. That's -1. And so even if x is negative, okay, this function is still going to give you 1 over x as the derivative. And so that is why this equation is true. And this is going to be one of the most important equations in the second half of this course. So keep that in mind. All right. Okay. Here's an example. Do you know what happens when you differentiate e to the x squared? Yeah, of course you do. You use the chain rule. It's e to the x squared times the derivative of this inside function. That's 2x, right? So based on that, it is okay to say that the indefinite integral of 2x e to the x squared is 2x. Sorry, it's not. e to the x squared plus c. No problem here. Okay, so this complicated looking thing has the indefinite integral. Now, what happens if you don't have the 2x? Can you think of a function whose derivative is e to the x squared? Think hard for about an hour, and then you come back after you think about this for an hour. Actually, pause this for a couple of years and come back when you find the answer to this. Actually, think of it for 10 years. No, the thing is, okay, I'm sorry about that. There is no such thing. There's no simple function such that, no function at capital F, such that the derivative of that is e to the x squared. So just because I can write this does not mean that there is an answer, or at least there's an easy to describe answer. So make sure you understand that. And for these, if you have to find the derivative whose, if you have to find a function whose derivative is e to the x squared, you may need to do something much more challenging. And so don't think just because you can write something, you can always find an indefinite integral. All right, the very last thing that I want to talk about is this thing called the initial value problem. Okay, so this is not going to take too long. But you know, for instance, s of t, if this is the position function, v of t is the velocity function, and you know that s prime is v, right? Okay, you take the derivative to go from s to v. If you take the derivative of v, what do you get? It's the rate of change of velocity, which is called the acceleration. And so v prime of t is the acceleration. All right, so for instance, right, if the acceleration can be written as 9.8 meters per second square, which is the gravitational force on Earth at sea level, technically, right? And also, let's say something is falling subject to the gravitational force. And let's say the initial velocity was 2. Okay, this is 2 meters per second. Okay, so something is, thrown down intentionally to the ground, and so the initial velocity, that force is 2 meters per second. All right. Now, can you find the velocity? So the velocity, okay, in order to find the acceleration from the velocity, you differentiate. If you are given acceleration, to find velocity, you take the antiderivative, right? The antiderivative of 9.8 is 9.8 t. Or is it? No, plus c, right? And then you plug in 0, you get 0 plus c, and that is given as 2 meters per second. So c is equal to 2, and therefore the velocity that you are looking for is 9.8 t plus 2. All right, so the point is, once you are given an initial value, which is the initial velocity in this case, you can actually decide what that c is, the constant. And so the answer turns out to be unique. All right, you will have a unique solution once you are given the derivative and a point, such as the initial point. Okay, so here's the velocity, right? And let's say this is the velocity function, and the position, maybe the height of this object being thrown down is 10 meters high. It's thrown down from a point 10 meters high above the ground or something. Then in order to find the position function or the height function, you again do the antiderivative of this. Now, what's the antiderivative of 9.8 t plus 2? Well, that's 4.9 t squared, right? You have to add 1 to the exponent of t. And when you differentiate this, you certainly get this. So that's no problem. And you have to have a 2t. And you have to have a constant. Now, this constant can be determined by, again, plugging in the initial value of 10. This is going to be 0 plus c, and that's 10. So now I know what this new c is. So therefore, now we have a complete description of the position function, which is 4.9t squared plus 2t, 2 being the initial velocity, and 10, where 10 represents the initial position, right? So once you have a derivative and a point or an initial value or some sort of a value of the function, then you can uniquely determine that C, and that is called an initial value problem. All right, I'm going to conclude section 4.10 and therefore chapter 4 with this one example of an initial value problem, maybe a little more abstract, okay? Find y, where you know that the derivative is x cubed and y at 0 is 5. Can you do that? Yeah, I think you can, right? Because what you can do is y happens to be the an antiderivative. It's actually the antiderivative of x cubed such that y of 0 is 5, okay? So what kind of a function has the derivative x cubed? Well, clearly that's x to the 4th. Well, not really. It's 1 over 4 times x to the 4th plus some constant, okay? But we are told that f of 0 is 5. So that means c must be equal to 5. And therefore, now we have a unique function that satisfies both of these equations, which is 1/4 x to the 4th plus 5. Okay, check it out. This is the only function whose derivative is x cubed and the initial value is 5. All right, so that, my friend, concludes chapter 4. Congratulations for finishing chapter 4, a very challenging and difficult part of Calculus 1. And now, next time we see you, we will start on chapter 5.